Hello everyone, I am Pushpita Chandra. I am a TA for today's session. I have discussed some problems on coherence time and coherence length, basically on coherence, in class 3 or session 3. I want to discuss the coherence thing a little bit more in this class. So, let us start. What is coherence? uh, to closely locate but separate laser beams on a single beam illuminating two closely positioned apertures. For that thing, coherence is very important. So for that, the important consideration in the study of lasers is the interaction of this two electromagnetic wave from these two lasers that are slightly different frequencies. In such instances, the two direct waves or beams will interfere with each other or to produce, in some cases, very dramatic effects. Such effects include development of longitudinal modes or mode locking or frequency multiplication as phase matching. So let us consider some two separate waves. Oops, with k vectors k1 and k2 and with angular frequencies omega 1 and omega 2. Both are traveling in the z direction. The electric field amplitude of such waves can be expressed as E1 is E1 naught e to the power minus K1z minus omega 1 t, and E2 will be E2z e to the power minus K2z minus omega 2t. Okay. So E1 naught and E2 naught represent the maximum value of the field amplitudes during their oscillating cycle. Okay. So the two waves to be closely located in space so that the combined E is equal to E1 naught e to the power minus I. So now intensity will be E whole square. So that includes E1 plus E2. That will be minus I K1 minus K2Z plus omega 1 minus omega 2 T I K1 minus K2 Z plus omega 1 minus omega 2 T. So this is equal to E0 1 0 whole square plus E2 0 whole square plus 2 into E1 naught E2 naught cos theta. We can write this term as a cos theta. Okay, because we know cos theta is equal to e to the power I theta plus e to the power minus I theta by 2. So here theta is k2 z plus omega 1 minus omega 2 t. This kind of calculation you'll be doing in the interference. Although there are in a conventional book, there are different kind of calculation for interference. But when you will study like what will be the fringe pattern of interference of one spherical beam and one planar beam, or spherical wavefront or planar wavefront, what will be the case, then this kind of analysis will be helpful. So if we assume now that E1 naught is equal to E2 naught, we'll see that values of theta near or equal to 0 or 2 and pi, intensity is 4 times E, not EI, because I1 plus I2 plus 2 E naught E2. So they and E1 naught is equal to E2 naught. So this become I. So E1 naught whole square plus plus 2 naught whole square is 2I. So this will become 4I. So this is 2 times higher of the sum of the intensities of two individual waves, right? Okay. And if theta is equal to pi, 3 pi, or you can say 2n plus 1 pi, 5 pi and so on, 2n plus 1 pi, then I will be not 0. Thus, the two waves are interfering with each other to produce effects not associated with each wave separately. So, looking at theta value is if the two waves have identical properties like K1 and K2 are similar, and if omega 1 and omega 2 are similar, then this interference are likely to occur. So then this two waves will be called covariant waves. Okay. So actually, no light source, however, emits a perfectly coherent wave. light waves which are pure sine waves only for a limited period of time or in time or in a limited space are partially coherent waves. So you will see that for only limited period of time and limited space, they are partially coherent. Partially because they are coherent in a limited period of time. That's it. Otherwise, they are called incoherent. Incoherent when k vectors k1 and k2 omega and omega 2 are drastically different, then they will not interfere. And are said to be incoherent. Okay. Now, period of time. So there should be a time that is coherence time and limited space that is coherence length. So for every source, there is a coherence time and coherence length specified. And upon like depending on this coherence length and coherence time, we uses these sources. Okay. For coherence, it would be I1 plus I2 plus 2 into E1 not E2 not for coherent sources. For incoherent, it will be like. So there are two different criteria of coherence. One is temporal coherence and another is spatial coherence. One is the criteria of time, is temporal coherence. Second is criteria of space, is spatial coherence. So, like I have discussed in the third session, that if a beam is originated at T1 time and another beam is originated T2 time. There is a time, okay, which is coherence time, that between these two times, if a laser source produce a waves, the two waves are said to be coherent. And also in a laser source, like here it is a point, here is a point. These two waves are generated from these 2 points. So distance between the 2 points L, which is coherence length, is specified for a space that if these two spots are within this boundary L, then only the waves will be coherent. Okay. So the temporal coherence. The case of temporal coherence refers to the relative phase or the coherence of the two waves at two separate locations along the propagation direction of the two beams. Okay, it's sometimes referred to as a longitudinal coherence. If you assume we assume the two waves are exactly in phase at the first location, then there still will be at least partially in phase in the second location. This distance is defined by coherence length. So you know coherence length or L, which is C into TC. That can be also given lambda square by delta lambda. Okay. And another is spatial coherence. This referred to as a transverse coherence. Okay. So it describes how far apart the two sources or portion of the same source can be located in a direction transverse to the direction of observation and still exhibit coherent properties over a range of observation points. This is sometimes also referred to as a lateral coherence. Transverse coherence, lateral coherence. So basically, let this is a source. Yes, there is 2 point. B. So the phase relationship between the points and B depends on the distance AB and the temporal coordinates of the beam. If AB less than LC, then there will be no definite unit phase relationship. And if AB is greater than LC, then there will be no coherence between the points A and B. Now, there is another point C, which is A and C are equidistanced from S. And if S is point source, then waves shall reach the points A and C in exactly the same phase. Okay. But if S is not a point source, sorry, the call rate got dropped. If S is not a point source, or S is a extended source, then A and C will no longer called coherent. Okay. Yeah, like we can understand the concept of coherence, time, and length. We can consider Young's double slit experiment. Okay, so this is a source S, then this is S1 and S2. This is screen P. Okay, so now we consider the interference pattern is observed around the point P at a time t is due to the superposition of waves emanating from S1 and S2 at times t minus R1c and t minus R2c respectively. Okay, where R1 and R2 the distance S1p and S2p. This is R1, this is R2. So time light needs to travel S1p is R1 by C and S2p is R2 by C. Okay, so interference pattern will be observed around the point P at time T is due to the superposition of waves coming from S1 and S2 at times t minus R1c and t minus R2c. Okay, if R2 minus R1 by C is less than tau C, then will be interference pattern. Okay. On the other hand, if the path difference is R2 minus R1 by C is greater than tau C, interference pattern not be observed. So next we consider Michelson interferometer experiment. So there is a light beam splitter beam gets slitted. This is a mirror M2 beam, and here is a mirror M1. They interfere, and here we see interference pattern, right? So this M2, the light can assume the M2 mirror is here in M1, M2 dash. So distance between M1 and M2 dash is D. Okay. So the mirror which gets reflected by the beam which gets reflected by mirror M2 travels an additional path equal to 2D. Like M1 and M2 are not at the same distance. If this is X and this is Y, then Y minus X is D. And this will also be Y. The additional path in M2 M2 arm is 2D. Okay. So the beam reflected from M1 interferes with the beam reflected by M2, which had originated 2 by D by C seconds earlier. If the distance, like 2D by C, is less than tau C, then only interference fringe will be observed. For this, there will be no Ferrell's fringes. Okay. Now, we have seen the young double slit experiment, like S1, S2, S. And here will be interference pattern on the screen P. Just a P dash, and this is O. Now we assume another source S dash the distance L from S. So we assume that waves from S and S dash are no different phase relationship. Thus, the interference pattern observed on the screen PP dash will be a superposition of intensity distribution of the interference pattern from D to NS and S dash. Okay. So S and S dash doesn't have any phase relationship. So the interference pattern will be superposition of the intensity distributions of the interference pattern formed due to S and S dash. Okay. If we increase L, then we can see that contrast of the fringes come poorer because of the fact that the interference pattern produced by S dash is slightly shifted from that produced by S. Okay. If S dash S2 minus S dash S1 is equal to lambda by 2. So the minima of the interference pattern produced by S will fall on the maxima of the interference pattern produced by S dash, and that's why no fringe pattern will be observed. Let's see. Vice versa. Also true. Like when maxima of S will fall on the minimum and S dash, there will be no interference pattern. So this is S dash. So this is S1, S dash S1, and this is S dash S2, right? So this is A1 and this is A2. The angle is here alpha, and also this angle is alpha, and the distance between S1 and S2 is D. Okay. And we can do the same experiment with extended source, like S and S dash is within a source. That's the thing. And that's criteria I will discuss later. Now, if S dash S2 is S square plus D by 2 plus L whole square to the power of S dash S1 is S square plus D by 2 minus root square to the power half. This is, we can say 1 by 2 a b by 2 plus l, and this is a plus 1 by 2 a b by 2 minus l. This is square. Okay. A is equal to a1 plus a2. So s dash s2 minus s dash s1 become l d by a. So a is greater than d and l. That's we have assumed. So LDA would be equal to lambda by 2 for fringes to disappear. Okay. So for L lambda by 2D. So if L is less than lambda A by 2D, we will get interference fringes with contrast. So here we have assumed that S and S dash is two different sources, right? But we can also assume that S and S dash is a part of extended source. That S is extended. So this is L and this is A. Okay. So we can consider L by A is equal to theta. So L by 2D. So L by A by 2D. A with theta lambda by D. So for good contrast, D should be L by less than lambda by theta. If it's D, then poor contrast. If we include the diffraction theory, we will get that D should be of 1.22 into lambda by theta or 2.25 lambda by theta and all that. And also that here we have obtained that lambda L should be of the order lambda by A 2D. The lambda by A to D, this L produces the fringes which are shifted by a half fringe width. So there, if L is lambda A by 2D, fringes are shifted by half fringe width. So so there will be no fringe pattern. Okay. So for visible fringe, fringe can shift a full fringe width. Then only for that reason, sorry, I'll wait. For that reason, when 2 into lambda A by 2D, that's become lambda A by D. That is when L is less than lambda A by D, we get fringes. Okay. Now, from this experiment, we also say that the size of the spatial coherence spatial coherence is related to the size of the source. Now, so if the spatial coherence is related to the size of the source, the temporal coherence is related to the monochromaticity of the spectrum. And we will prove that. Okay. So we know that every spectral line has a finite width, which means it corresponds to a continuous distribution of wavelength in some narrow interval between lambda, lambda plus minus delta lambda. This is obvious from the fact that so for every spectral line, the interference pattern in the Michelson interferometer experiment eventually disappears when the path difference between the interfering beams is gradually increased, and the pattern disappears when the path difference exceeds the coherence length. Thus, the concept of temporal coherence is directly related to the line width of the spectral line. Michelson. Okay. So we adopt a criteria that when the path difference between the interfering beams becomes equivalent to the coherence length, the ring is due to two closely separated wavelengths. The rings due to the closely spaced wavelengths lambda 1 and lambda 2 are completely out of step at the center. That is, bright ring of lambda 1 coincides with the dark ring of lambda 2. Okay, so the when path difference between the interfering beams become equal to the coherence length L, the rings due to two closely spaced wavelengths lambda 1 and lambda 2 are completely out of step at center. So, which means right ring of lambda 1 coincides with dark ring of lambda 2. Then we can write L, which is the path difference. of coherence length to n into lambda 1. Okay, coherence length n plus half into lambda 2. So we get eliminating and we get L is equal to L by lambda 1 plus half lambda 2. So it will be L lambda 2 minus L lambda 1 is equal to half. It is lambda 1 minus lambda 2, lambda 2 is equal to half. So LC will be lambda 1, lambda 2, lambda 1 minus lambda 2 into 2. So it will be lambda square 2 into lambda 1 minus lambda 2. Okay. So if instead of two discrete wavelengths, lambda 1 and lambda 2, the beam consists of all wavelengths lying between lambda and lambda plus delta lambda. Then the pattern produced pattern means lambda and lambda plus delta lambda by 2 would disappear if C is equal to lambda square 2 delta lambda, which is lambda square delta lambda. From this, we get a formula that coherence length is lambda square by delta lambda. Now, for each wavelength lying between lambda and lambda plus half of lambda, there is corresponding wavelength such that the minima of one fall on the maximum of the other, causing the fringes to disappear. But the fringes will have a very poor contrast when L is greater than lambda square delta lambda, or delta lambda is greater than lambda square by LC. So delta lambda should not be equal to lambda square by L. So the spectral line width should not exceed lambda square by LC. Okay. Now we know delta mu is C by lambda square delta lambda minus there. So minus mu is equal to C by lambda. Delta mu is equal to minus C by lambda square delta lambda. So when we take what it will become. Okay. So this is become C by LC. And for its time, delta mu tau C is equal to 1 by delta mu. Okay. So for a cadmium light, 9 lambda is 6438 angstrom and LC is about 30 centimeter. So delta lambda should not exceed or equal to lambda square by LC, which is 6438 whole square by 30 into 10 to the power 8. All things should be in angstrom. So this is 0.0 angstrom. Okay. For sodium yellow line, lambda is about 5893 angstrom and LC is equal to 3 centimeter. So delta lambda is about 0.1 angstrom. But it's vice versa, that for 0.1 angstrom we get a coherence length like this. Okay. So delta nu is equal to 1 by Tc. For perfectly monochromatic light, delta nu should be 0. So Tc should be infinity. But for ordinary source, tau is equal to 10 to the power minus 10 second. So delta nu will be 10 to the power 10 hertz. For sodium yellow line, lambda 5893 angstrom. So mu is equal to C by lambda, which is 5 into 10 to the power 14 hertz. So delta nu by mu was 10 to the power 10 hertz by 5 into 10 to the power 14 hertz. So this is equal to 2 into 10 to the power minus 5. This value delta nu by mu is monochromaticity. That represents monochromaticity. For laser beam, delta nu by mu is 4 into 10 to the power minus 8. So that's all the theoretical discussion. Now let us discuss some problems. Like some problems has been discussed in TA session 3. And some I'll be discussing. It's a line width of in terms of length. So delta lambda is 0.018 angstrom. Laser line widths as low as 20 hertz occur. Calculate the coherence length. So delta screen to respond. Example 3. Like the coherence time for lead cadmium line is lambda 6438 angstrom, is about 10 minus second. Estimate coherence line and coherence time and lambda is given. Estimate the monochromaticity of the line. So delta mu is equal to 10 to the power minus 9 centimeters. You need to calculate mu. Mu will be C by lambda, which is 3 into 10 to the power 8 meter per second, and 6438 into 10 to the power minus 10. This will be 4.66 into 10 to the power 14 second inverse. This will be 10 to the power minus 9, 4.66 into 14 second inverse, which is 2 into first house is equal to 10 to the power minus 9. 2 into 10 to the power minus 6. This is answer. Now, an interesting question. The sun subtends an angle of about 32 inch on Earth. Suppose sunlight is falling normally on Young's double slit arrangement, having a filter which allows only light of wavelength 5000 angstrom through it. What should be the separation between the two slits in order to obtain good contrast? Fringes on the screen. So alpha is 32. So that will be 32 degree. Just pi 180 32 60 squared. So it will be 0.009 almost. So spectral coherence we have obtained here. Theta so we know L should be lambda A by D. Okay, so D should be lambda A by D. Theta was L by A. Theta. So D less than lambda by theta. So distance here theta is alpha, which is equal to 0.09 rad. Okay. So the separation D should be lambda by alpha or theta, whatever you say, is 5000 into 10 to the power minus 8 centimeter, 0.009, which is about 0.005 centimeter. This is the answer. Okay. Now let us discuss some other problems. So example 5. LC of temporal coherence length of mercury vapor lamp emitting in the green portion of the spectrum. The wavelength 546.1 nanometers with an emission bandwidth of delta mu 6 into 10 to the power 8 hertz. And helium muon is operating at a wavelength of 632.8 nanometer with an emission width of delta mu 10 to the power 6 hertz. So need to obtain temporal coherence length. So delta lambda for Mercury upper line is 546.1 to 10 to the power minus 9 whole square into delta mu is 6 into 10 to the power 8 second inverse and 3 into 10 to the power 8 meter per second. This is equal to 5.96 into 10 to the power minus 13 meters or 5.96 into 10 to the power minus 4 nanometer. So now for Lenz's length, we know lambda squared by delta lambda. Then we need to put this value. It's 0.50 meters. For helium neon, laser delta lambda is again lambda square delta mu by c is 632.8 into 10 to the power minus 9 meters square into 1 into 10 to the power 6 second inverse 3 into 10 to the power 8 meter per second is equal to 1.33 into 10 to the power minus 15 meter 0.33 into 10 to the power minus 6 nanometer. So temporal equivalence will see equal to lambda square by delta lambda 633.8 into 10 to the power minus 9 meter whole square 1.33 into 10 to the power minus 15 meter just 301. So for cadmium light, the coherence length is 0.50. For helium neon, oh no, sorry, for mercury, the coherence length is 0.5 meter. For helium neon, it is 301 meter. So for kind of experiment point of view, helium neon lamp is laser is much more, what should I say, like easy to handle. Okay. Example 6. A laser produced plasma consisting of 100 micrometer diameter ball radiates very strongly at a wavelength of plasma consisting laser of 10 nanometer at a distance of 0.5 meter from the source What is the spatial coherence resulting from light emitted from opposite sides of the plasma? Remember this thing D, the size. Okay, the spatial coherence length, you can say. Okay, so here it is L T is equal to lambda, sorry, not this. This is spatial coherence length. So here it is A by D. So here this is S. Sorry, G. When the source is like this, R usually signal distance is Meaningful violation of resistance and to superintendent's pattern of effects at point A. So if the two sources uh, are in difference with S and an interference pattern is observed at a distance R, then this will be LT. The coherence length is where D is the longitudinal coherence length actually. D. This is the coherence length. This is S. This is a distance R. So there will be another thing. LT. So the two sources exhibit interference effects at point A, then the transverse coherently is the transverse distance from point A to B, where the two sources cease to show from this A to B. Here, to A to B, two sources separated distance will show interference pattern. It's 0.05 into 1 into 10 to the power minus 8. Use 1 into 10 to the power minus 4. So this will be 5 into 10 to the power minus 5 meter. This LP is called, so this is the answer. This LP is called transverse coherence length. Here, is called transverse coherence length. Now, you want to some simple experiments, the sheets. Sample 7. a laser beam of wavelength 6328 angstrom, power 10 milliwatt, and angular speed spread 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 5 into 10 to the power minus 5 rad is focused by a lens of focal length 10 centimeter. Find the radius, power, density of the image and coherence width. So lambda is equal to 6328 angstrom. Okay. For, or it can be 6328 into 10 to the power minus 8 centimeter. Power is 10 microwatt. Is 10 to the power 10 to the power minus 3 watt. Angular spread theta to 1.5 into 10 to the power minus 5 rad. F is equal to 10 centimeter. So radius of the image is equal to r theta, which is 10 into, like L is equal, D is equal to L into theta. L is equal to focus length 1.5 into 10 to the power minus 5. So this is 1.5 into 10 to the power minus 4 centimeter. Area of the image into r square. Power density will be intensity by area. Just so power density equal to 10 into 10 to the power minus 3 pi into 1.5 into 10 to the power minus 4 whole square. This is equal to 14447 into 10 to the power 3 watt per centimeter square. Coherence width will be lambda by theta, and this is also the longitudinal, the transverse or the spatial coherence length. Two six three two eight into 10 to the power minus 8, 1.5 into 10 to the power minus 5, which is 4.22 centimeters. Then example 7. At what temperature the rates of spontaneous emission and stimulated emissions are equal. Lambda is equal to 5,000 extra. Okay. This emission and stimulated emission will be equal when 1 by E H nu by K T minus 1 will be equal to 1. So E H nu K T will be 2. So H nu K T will be ln 2. So H nu will be K T ln 2. This is H C by lambda K T ln 2, and T will be H C by K ln 2 this. So putting all the value here, 6.626 into 10 to the power minus 34, 3 into 10 to the power 8, K is 1.38 into 10 to the power minus 23, ln 2 into 5,000 angstrom. This is 4156. 41562.1 Kelvin. Okay. The last question. This was example 8. Number line. Example 9. Calculate the ratio of spontaneous emission to stimulated emission rate at T is equal to 10 to the power 3 Kelvin for visible light of frequency 5 into 10 to the power 14 hertz and with frequency 10 to the power 9 hertz. So R exponential h nu k t minus 1. Okay, this is the ratio of the spontaneous emission to stimulated emission. So this will be 2.67 into 10 to the power 10 for visible light and 4.8 into 10 to the power minus 5 for microwave. See, it's all for total. Let me check. Total emission, spontaneous emission. Here it is not like this, it is like this. That's for today.